Good afternoon, everybody. Welcome to Windows 10 mitigation improvements. You are in Mandalay Bay, GH, with David Weston and Matt Miller. Before we begin, just a couple of notes just before lunch. Please make sure you stop by the business hall, which is located downstairs in Bayside AB. The Black Hat Arsenal is on the Palm Foyer on level 3. That's upstairs. And, of course, there's the Arsenal reception tonight at 5 p.m. If you haven't picked up your merchandise, today is your last day to visit the Black Hat Swag and Bookstore. Also, make sure that you visit the Kali Linux Lab over in Mandalay Bay A, which is down the hall just a bit. Thank you also for putting your phones on vibrate so that you don't disrupt the talk. We really appreciate your cooperation. So without further ado, here are your speakers. Thank you very much.
Thanks very much. So my name is Matt Miller. I work in the Microsoft Security Response Center. So I get to see all the vulnerabilities that come in the door that get reported to Microsoft and try to drive change and make our products better.
I'm Dave Weston. I lead the Windows Offensive Security Research team. I have the privilege of writing exploits as my primary job.
So quick summary of our agenda. What we're going to do today is tell you a little bit about what we call our data-driven approach to software defense at Microsoft. And we'll tell you how we use data to craft how we make improvements to our products. And furthermore, we'll talk a bit about how we've adapted kind of traditional red teams to the software space to help accelerate learnings and improve defense so that we aren't just looking at what attackers are doing in the wild. And finally, we'll talk about all of the latest and greatest mitigations that we've added in Windows 10 to help improve software security.
And we all know what the most important mitigation is in Win 10, right? We removed calc. So many POCs mitigated by that.
With that, I'll hand it off to Dave.
All right. So the first thing I kind of want to talk about is the problem space here and how we've driven so many mitigations into Windows 10. So the traditional software security approach, a lot of it pioneered by Microsoft, is a secure development lifecycle process, or SDL at Microsoft. And the goal of that originally, when we started initiating deep integration of security into our engineering process, was to essentially find all the bugs. And obviously there's different methods of doing that. That includes design level flaws that you might uncover through things like threat modeling, static analysis that'll remove really low hanging fruit from a developer kind of mistake standpoint, and of course things like fuzzing. So our approach originally was just find all the bugs and everything is great. Now the tough part about that is you can do an excellent job at finding all the bugs. You can find 99.9% of them, but that 0.1% is going to leave a lot of opportunity for attackers. And that's one of the problem spaces that we started to analyze when we were looking at how can we augment our previous security investments. The other challenge with preventative security is that it's very focused on integration to engineering teams, right? We want to scale a software security process across this, at least at Microsoft, this large machine. We've got armies of developers. And so when we institute security programs, it needs to scale there. We need to take into account how do developers write code, how do they test code, how do they check in code. And so a lot of the SDO and preventative processes are goaled around making it simple to put into the process. Now the challenge with that is a lot of it becomes static because you want to make very simple rules that anyone can adopt. But we know in the real world, attackers are able to quickly identify those rules and move around them. So that's, again, another problem space that we identified. And one of the reasons and one of our goals with mitigations is to augment there. Another interesting thing is in the engineering process, you have teams who are sort of organized around the components they build. So it's very difficult for them to get a holistic idea of the process. They're focused on the binary, the library, the feature, the app that they write. They're not necessarily looking across scope. Additionally, in a complex product like Windows, we're taking contributions from partners, so third-party vendors, et cetera. The traditional preventative security process doesn't account for all those soft edges between the various silos there. And so, again, attackers are experts at finding places where we've misidentified or failed to find a potential integration issue or a gap, and we were looking at solutions for that with our mitigation strategy. And so a couple of other things that are we noticed that don't fit well with the attacker model of security and our traditional model of preventative security. And the first there is attackers are really agile, they're adaptive, and they're results focused, which means if you have a deeply integrated sort of engineering-focused software security program, it can be really difficult to match asynchronous or asymmetric attackers who are moving very quickly. If you've got this giant kind of aircraft carrier going in one direction and they're in speedboats, that's going to be difficult to account for in a pure preventative strategy. The other challenge with, in my opinion, with preventative security is that it's, again, very vulnerability focused. Now, what's the challenge with that? When we look at the cost to attackers, arguably the vulnerability portion of that is the cheapest. And if that's exemplified in basically market value, right? You can sell our remote code execution vulnerability in, say, Microsoft component from somewhere around 3 to 4K, maybe up to 15K, depending on the bounty program you report to or the vulnerability buyers you're dealing with. We see exploits at 10x that. And what that tells us is that the market, or the attacker market, is really valuing mitigations and some of the security features, isolation, all sorts of things, as the hard part or the costly part or the disruptive part of actually building attacks against customers. Additionally, attackers, again, really view vulnerabilities as fairly fungible. What we see in the most of the most mature attackers is that they're investing in libraries of techniques. So maybe they have a technique around ASLR, maybe they have a ROP technique, maybe they have a technique even for escaping the sandbox. And they, of course, invest in those, and they build mature models, they build libraries, they do everything standard development teams do. And so with vulnerabilities, you're not really disrupting that huge capital investment. Instead, you're making it slightly more difficult in some cases for a good team at finding vulnerabilities to find sources for that investment, but you're not really disrupting their biggest kind of value proposition. And then finally, arguably, in my opinion, the most difficult part of preventative security, or the biggest challenge, is you don't know how well you're doing. So you don't know if you found all the bugs. You don't know if you found 99%, and the attackers are just kind of plying their trade or their tradecraft on that remaining 1%. And so you don't know how well you're doing. And so the combination of these challenges with preventative security, when Matt, myself, and many other folks at Microsoft are looking at how to augment it, is we start to look at, let's just assume there are bugs. Let's assume there are going to be opportunities for vulnerability and exploitation. Let's just take an assumed breach model and then look at what we can do starting from there. And so that drove us into what we're calling a data-driven software defense process that essentially assumes that vulnerabilities will be there and starts to orient our defenses and our investments around dealing with that new reality. So the first thing we do in this data-driven defense model is we're analyzing real-world data. So we're very comprehensive in sourcing all of exploits across the Microsoft partner ecosystem, our telemetry sources, and of course MSRC, and folks in this room who are reporting vulnerabilities and exploits that way are a big part of that. But our goal with this portion of the software defense, data-driven software defense model, is to get as much real-world data as we can to identify opportunities and huge areas of ROI for attacker disruption and strategic hardening investments. The next step is the same security engineers who do that analysis begin to build defenses. And we think that's a critical part of what's made this strategy successful, and some of the arguments I'm going to make going forward is we've moved away from security engineers just finding vulnerabilities, just being involved in the fixes, and they really are wearing a pure engineering hat. A lot of the mitigations we'll show you and the improvements that we made that have been most disruptive are actually made by folks who are, maybe security people by trade, but have expanded their skill sets into being really robust engineers. And they're often at the front end of a very interesting or novel idea, building out prototypes and then working with software teams in partnership to build mitigations and defenses. And then finally, a very new sort of development is we are evaluating these mitigations. So just to refresh, we've analyzed maybe a huge exploit set to say what techniques are most frequently being used in, say, attacks against Internet Explorer or other browser components, attacks against the kernel. We're identifying and building prototypes that we think will disrupt attacker investments there. And then before we ship it out to 1 billion folks, we need to evaluate it. So how do we evaluate it? Well, what we've started to do is put on an offensive hat and say, let's model the same things that attackers are doing. Let's start to project and do a bit of game theory and say, let's build an end-to-end exploit and let's see how these defenses stand up. And so this whole suite of mitigations that we're going to talk to you a bit in this talk have undergone this process, and we think that the proof's in the pudding, and we've got some interesting results to share. So I want to talk to you a little bit about the high-level part of this process. So we have a whole bunch of external data sources, as I mentioned. So we have huge telemetry investments MSRC has been a long-standing kind of pillar of partnership between Microsoft and the external world, receiving a lot of reports, a lot of good partnerships with folks in this room. We've augmented with things like the Microsoft Threat Intelligence Center, who have threat intelligence partnerships where we can get word of essentially exploits. But and obviously we also have open source analysis. We look at social media, et cetera. But our goal here is to get the most comprehensive data set available so that we can do the teardown and identify places where we should be investing going forward. And we've moved away from sort of, it'd be cool if we had a mitigation to do this, to let's actually identify the problem empirically and produce a solution that's going to have a pretty well-defined return on investment. We've also augmented that with internal sources. So I'll talk to you a little bit about anecdotally. Some of the competitions out there have been for exploit development have been really helpful in providing responsibly disclosed exploit techniques that we're able to figure out and identify ways to mitigate. And so we've picked that up internally and said, well, let's just run our own essentially exploit competition all year long on these key scenarios. And the exploits and techniques that are developed there become inputs into this overall process. In this multidimensional exploit analysis process, we're looking at what are the root cause similarities across these bugs. So is it UAF? Is it a type confusion bug? Is it an integer overflow? And we get actually pretty granular and pedantic in this case because what we're looking for is sometimes, in some cases, micro trends where we're saying, look, this looks like it's starting to emerge. So in the next 6 months, we really need to have some sort of a vulnerability class level mitigation for this emerging trend. Of course, we look at things like exploit techniques. So are folks using heap spray? So what are they using to do information leaks? Are they creating RW primitives with a particular length field and a particular type? And then we reason about, can we create a durable mitigation that will help here? We track attack surface, so what components are most frequently being targeted? Is there a particular 3D graphics library or something like that that has an emergent trend? And we're going to focus our investments in those areas. And then finally, we're trying to analyze in the real world from these data sets what mitigations are actually the most impactful. So this looks kind of glamorous, and I know these 3 boxes look very advanced, but it's actually pretty tedious work. So I call it like the monkey model or zoology. Like, how do you understand the behaviors of monkeys? Well, you write down the monkey pooped at 10:20 p.m. The monkey ate a banana at 10:23. And a lot of this exploit analysis is that blood, sweat, and tears of every time an exploit comes in, you're doing the hours of teardown, and then you're meticulously documenting each piece. But the outcome of that is actually some very powerful data. And so what you'll see throughout these slides interspersed is our ability to say specifically how many exploits would be impacted by a particular mitigation, what drove it, what data sets, et cetera. And so that's opened us up, I think, in a lot of cases to have a lot more impact, at least across our product set, because when we're going to management and asking for an investment, we're speaking with very detailed reports. So what does that look like in terms of impact? Well, on your left, you can see a chart there that's essentially the number of RCs that are being reported to Microsoft. And you can see that there's a huge number of essentially unique CVs that are growing. So we've got a lot of growth there. Now, you would think just intuitively, if there's a lot more vulnerabilities being reported, there's a lot more risk or a lot more exploits in the ecosystem. But what we can prove empirically is it's actually the opposite. The potential risk is going up, but the real-world risk of actual exploits is going way down. And our answer to that is we think we're onto something with this mitigation investment or our data-driven software defense strategy, which is there's certainly going to continue to be bugs and opportunities to attack stuff, but we really funneled it down to an elite few who can actually bypass all of the mitigations that are in the box and develop exploits that impact customers. And so we want to focus on this increasingly small number of capabilities, techniques, et cetera, and kind of wind those down. And that is our strategy all up, and we think that we're onto something, and we're going to detail the process a bit more. So what does this look like in practice? So what I wanted to show you guys was some of the behind the curtains of how we develop exploit mitigations. In this case, this was in partnership closely with Adobe, so we worked with those folks quite a bit to bring some of our experience and our kind of battle scars and work with Adobe to implement some of the strategies that we've seen successful. So the first chart here is an example of the kind of analysis we can do. So we took a data set of essentially 2 years of in-the-wild exploits, and we broke down, again, in this very pedantic manner, all of the different attributes of these exploits. And what we noticed is that there was a very strong trend, and I think it's somewhere over 85% of the exploits we looked at in this 2-year period in the Adobe world were creating what we call read-write primitives or RW primitives through vector length corruption. That's a very powerful primitive that allows you in some cases to bypass many platform mitigations. And so when we sat down to talk with Adobe and other folks about what we could do to improve the security of Flash against exploits, we looked at this data, and it wasn't very difficult to spot where the opportunity was. Now, this might look very simple and kind of obvious to everyone out there, but this was a powerful capability. And if we hadn't done all that data entry and all those things, and this is not something we'd always done historically, it wouldn't have been as simple to figure out, look, if we mitigate this, we're going to really disrupt that attacker ecosystem and a lot of those ActionScript-based libraries that were built around specifically doing array-linked corruption. And so we partnered with Adobe to do similar mitigations in both the byte array object and vector length, and introduce an integrity check there that did have some disruption that we observed in the ecosystem. Similarly, we looked at the root cause of all these different vulnerabilities that were exploited in this 2-year period. And what we found was that there was a strong trend around what we call linear heap corruption. So that's where essentially you're overflowing an allocation on the heap. And a traditional defense that we knew might be powerful there, once we understood how strong that trend was or how prevalent it was, is we worked with the Adobe folks to introduce the Windows heap as the primary allocator in Flash on Windows. And that gave them some what we call heap randomization or subsegment randomization, which makes those types of vulnerabilities, linear heap corruptions, much more difficult to exploit. So those are 2 examples of where we were able to take data analysis and build some prototypes or work with partners to do that. And we've seen some pretty strong impact overall. Another place where we have some evidence that we're onto something here is in Internet Explorer. So what you see up here is a timeline of essentially known exploits against Internet Explorer in about the last 3 years or so. And what's interesting is you can see there at the early 2014, objectively, Internet Explorer was in a pretty bad position in terms of security. We had 4 0 days in a row that had caused major organizations and governmental bodies to come out there and say, we can't recommend IE. And so that was a huge concern both on the business and the customer security side. The interesting thing is that's also exactly the time period when Matt and I got the job to work on Internet Explorer security. So it was a fun time to take that job. And what we did is we quickly implemented this data-driven software security strategy, which is we looked at the bug trends and saw that they were pretty much standing still, or that they were equivalent. And so we didn't think necessarily just doing more preventative security would get us the results we wanted in Internet Explorer. So we took a very different tact, which was we analyzed the historical exploits, including the recent 0 days, and we reasoned about a package of mitigations that we could immediately start shipping out into the wild to have some impact and some disruption. And back to those problems I talked to you about, which is what are the techniques that attackers have capitalized on and built serious investments on. We know if we break those, we'll at least have some leeway to make further improvements because folks will be disrupted either permanently or at least in the short term. And that what we saw there is great results. So when we started in early 2015, there had been 135 days of 0-day exposure to customers. And that means 135 days we knew that an exploit was in a while where we hadn't yet issued a patch, which is not great. After shipping this series of mitigations, we took that down to 45. And that's without necessarily doing more preventative security, although that was an investment as well, but roughly the same number of bugs in that period. And so what we decided on is mitigation was the key factor in the 0-day reduction trends here, and we wanted to continue that investment. So we looked even more for inspiration across our own company, which was in the network services space. The interesting thing I observed in the network security space, and this is a learning I had, which is look more at the places that you don't necessarily think are exactly tied together, but they had some really interesting approaches there. So the network folks had sort of long given up on closing every potential hole into a network. Instead, they were saying, look, if people are going to get in, let's focus on how fast we can detect them, how fast we can contain them, and how fast we can respond. So really, in my opinion, a mature way of looking at the security problem. And so we also thought that this old school red team kind of mentality, when I say old school, is we've had operational security red teams for a very long time, but it's actually not very common in the software security space. In fact, I can think of only a few sort of major software vendors that have people who specialize in exploitation or software-focused offensive security. And so our approach was, we think we can take this same assumed breach model and use that to proactively attack ourselves, right, our software and models, identify the same type of mitigations that we were doing reactively with data sets, and make that work. Now, what was our inspiration for this? So we had a lot of luck and got a lot of value off of the pwn to own competition. So every year, for those of you who don't know, there's sort of a grand championship of hacking, at least in the browser space, called pwn to own. And folks from around the world come and exploit browsers. And as I said, that's really a technical feat at this point because we've reduced the number of people who can actually bypass mitigations in modern platforms to a very small percentage. And so every year, we would kind of hang out and wait for these exploits to come in, and we'd tear them apart the second they came in, and we'd make all kinds of improvements. So this list here is just a few places where either we were inspired based on analysis of a pwn to own exploit, or we were further kind of evangelized, or we were able to work with management to say, see, what we were saying is true. We're seeing these kind of techniques used in the wild. And we were able to land a whole bunch of improvements. So the traditional challenge with this assumed breach model in the software security is you don't write exploits. That's kind of sacrilegious in some circles. And so without that, your mitigations are working, but you're waiting for someone else to develop them. So we needed to solve the problem of how do we do this proactively without everyone sort of going nuts. And I'll tell you, the first time I went to my management was like, hey, I would like to form a crack team of hackers who write end-to-end full zero-day exploits against our own software. They looked at me like I was nuts, right? And so after I showed them this kind of data, people said, you're onto something here. And so we wanted to move away from just waiting for in the wild exploits to doing them ourselves. The other advantage that this gave us, which is significant in my opinion, is while developing an exploit, we can track how costly it is in terms of time resources. So, for example, if it takes us 200 days to write a zero-day exploit, and we do a bunch of mitigations in response to the techniques or the gaps that are uncovered there, the next year you would expect that to be 400 days and et cetera. So it gives us a very concrete based time metric in which we can gauge the relative value of a security mitigation against. And that's something we can't do when external people are actually developing it. So the goal here was to figure out how do we do that proactively. And the end result is we formed a red team on the Windows side, very similar to what we have in our Azure cloud space, our O365 space, that are focused on services pen testing. So our goal with this team was to model real-world attacks. So we wanted to do things like take some of the techniques that are out there, or at least some of the approaches, whether that be spear phishing, whether that be a watering hole attack, look at some of the techniques from various groups, exploit kits, APT, et cetera. Take some of that, internalize it, and focus. The way that we chose to do that, at least in Windows, is we take a very large scenario, and say, red team, you're just open to attack it. So it's as long as it's in the default configuration and it's not, some sort of thing that wouldn't impact all customers, you can target it. So we take these very large scenarios, and that includes inbox binaries. So that solves some of the problems I was talking about in preventative security. They can take bugs that we found in other preventative security, maybe we haven't fixed yet through fuzzing investments or access there. But really, we're focused on saying, let's just assume that you're a well-funded and advanced attack group, and let's go and target some of these scenarios. And so we think that sort of full scope thinking and the agile thinking that's closer to what attackers, how attackers approach the problem, are able to expose gaps. The next thing we do upon a successful mission is we look at what we call the medium time to pwn, or the medium time to compromise, which is how long did it take us to compromise this key scenario. And we want to look over time at hopefully increases in that metric, but this gives us that real world at least metric that we can shoot for in the future. Additionally, many of you know that an attack is not just a software or a technology problem, it's a process problem. So if we're taking a feature that hasn't been exposed to the world yet, and we write a zero-day against it, and we test it, we should simulate basically our incident response processes and make sure they know who to call. What do we do about this? What about this third-party binary? Should they patch it? Should we? Do we have the right controls in place to actually stop this before we patch it, et cetera, et cetera? So we've started to use these red team operations and the outbriefs as essentially simulated software security incidents, and we've seen a lot of value out of that. The other thing we're able to do here is take some of the invariants of the attack and work with our blue teams to provide proactive detection. So if there's a new exploit technique or something like that, we can hone in on that generic piece in whether it's in our Defender Advanced Threat Protection product, our Defender Anti-Malware engine, or just log IOCs, things like that. We can shift those around to various teams. And finally, like I said, we can demonstrate impact. So if we did this, year one, we should be able to come back year two and say, we implemented all the controls and all the mitigations that were suggested, and the end result is, the MTTP went way up. So we think that that's been really valuable so far. And if you're interested in how our folks over in the Cloud Services division do that, I recommend the paper there at the below from Mark Rusinovich. So how have we done? Well, I would say the offensive security research team has been operating about a year, which is our red team. We've exploited 4 to 5 different scenarios that we don't know of real-world exploits for, and that have given us opportunity to go and understand and implement mitigations there. And a lot of the work you'll see here was at least partially influenced by some of that analysis. We've also been able to share a lot of that information with our blue teams and make sure that going forward in the places where we don't have a complete mitigation, we at least have partial detection strategies over. And the end result is we think that this entire process is now very mature and has become at least a core pillar of the Microsoft security strategy all up. So with that, I'm going to pass it over to Matt to talk to you about some of the end results of this type of work.
Thanks, Dave. So as Dave showed, using kind of this data-driven approach and using Red Team kind of really helps us hone in on the important areas that we want to invest in for mitigations. And by having this Red Team on hand, it really accelerates the process. We don't have to wait for Pwn to own. We don't have to wait for an exploit in the wild. We can actually learn much more quickly, and it's really been a big boon to us. So in this part, we're going to start talking about improvements that we've made in Windows 10 to really up the game in terms of mitigations. So as we've talked about, we make what we call kind of like a layered, data-driven software defense approach in Windows 10. And our strategy at a very high level is one that we've been following for quite a few years now, which is we want to make it difficult and costly for attackers to find, exploit, and leverage software vulnerabilities. And the tactics that we use, which I'm going to talk about in more detail, are one, we eliminate the classes of vulnerabilities, or look to eliminate classes of vulnerabilities that attackers might want to take advantage of. We break the exploitation techniques that they want to use. We contain the damage and prevent persistence, and we limit the window of opportunity to exploit. I'm going to go into more detail on what each of these actually means here in a moment. Before we go into detail, we're going to read every name on this slide. No, actually, we just want to acknowledge that a lot of people view Microsoft as a black box, but it really takes a ton of folks to ship the features and improvements that we make here. So a lot of people have contributed. Dave and I happen to be the ones up here talking, but a lot of people have made this possible, including the folks that have participated in our mitigation bypass bounty programs. They've really helped us up the game too. So thank you to everybody. So first off, we want to talk about the tactic of eliminating classes of vulnerabilities. And the way that we look at this is this allows us to move beyond what we call the hand-to-hand combat of, somebody reports a vulnerability, we fix it. This is a way for us to actually go and get ahead and just cleave off an entire class of vulnerabilities so that we don't have to deal with them anymore in the future. And you can think of this as the goal here is we want to increase the attacker's cost of finding a vulnerability in the first place, which is a great place to start from if you can get there. So as Dave mentioned, one of the ways that we do this and make sure that we're honing in on the right areas is that we closely study the vulnerability root cause trends. We've got a lot of great and talented security engineers at Microsoft, and when vulnerabilities come in both internally and externally, we categorize the root cause of every single one of those vulnerabilities, and we look for patterns. So for example here, what this chart is showing is the volume and the absolute amount of different types of RCE vulnerabilities that affected Windows, Internet Explorer, and Edge over the past few years. And if you hone in on 2013 and 2014, you can see that there was actually a huge spike in use after free vulnerabilities. And this is something that really stood out to us. So some things I'll call out. Up at the top of the chart in light blue is stack corruption. And what you can see here is that it used to be the case that stack corruption was a big chunk of the types of vulnerabilities that were reported to us, but now they've essentially been eliminated. People aren't finding and certainly aren't exploiting stack corruption vulnerabilities anymore in Microsoft products.
We have this big red light that comes on in your office when you try to check in stir copy or something like that.
Yep, exactly. As I mentioned, so use after free issues rose dramatically in 2013 and 2014, but they've really dropped off substantially, and we'll explain why that's happened here in a moment. And we also noticed some trends pop out where heap out-of-bounds reads, type confusions, and DLL planting issues have all increased, and we'll talk a little bit about those as well. So when we studied those trends and we saw that increase in use after freeze, we realized that we really wanted to make a big investment to go and address that entire problem class to the extent that we could. And one of the investments that we made is something that we call memory garbage collection. And so when we dug into these use after freeze, we found that actually the majority of them were use after freeze in the DOM engine of our browser. And the way that MemGC works is, if you think about the world without MemGC, a traditional use after free works something like you allocate some memory, later on you free it, but unfortunately you forgot to zero out that reference to that original allocation, and then you use that object after it's been freed. And in between step 2 and step 3, the attacker reallocates that memory to some other type with data they control, and that allows them to take advantage of it. With MemGC in place, what ends up happening is at step 2, rather than deleting and actually freeing the object, all we do is zero it. We zero out the contents, and at some point later in time we'll do a garbage collection pass. So it's just your normal garbage collection. And if there are any references to an object, such as in the above example, we actually won't free it. So this entirely mitigates these classes of vulnerabilities that involve use after free through the use of a conservative garbage collector. One of the things to call out is that although we initially shipped this in Edge in Windows 10, we actually went and backported this to all the supported versions of Internet Explorer. So it wasn't just Edge that benefits from this, it's all the in-market versions.
And shipping stuff like this is always a lot of fun because we get to monitor Twitter and see a lot of sad people who have their bugs killed. Does anyone have their bugs killed by MemGC? You don't want to raise your hand. Okay.
So that's MemGC. As I mentioned, we noticed also that there was a trend where type confusion vulnerabilities were increasing. And so what we did is in late 2014, we started investigating some of the sub-patterns of these type confusion issues that were being reported to us. And what we noticed is that about 50% of those type confusion issues were due to bad casts. The developer was casting objects between different types that was incorrect. And we dug in a bit deeper, and we found that about 50% of those bad casts were due to recurring patterns. And so what we did is we actually went and introduced additional checks into these places where that were operating on these objects to basically eliminate that subset of type confusion issues. So we went and killed off about 50% of the type confusion issues that we were seeing reported to us. So another way that we can help eliminate classes of vulnerabilities is, of course, attack surface reduction. And in Edge, we really took the opportunity to go and eliminate a huge chunk of the attack surface that was traditionally exposed to the web. So no legacy document modes, no legacy script engines like JScript and VBScript, no vector markup language, no toolbars, no BHOs, no ActiveX. Tons of code was removed, and we really were very happy about that. Now, like we said, we're data-driven here, and we want to measure our success. And one of the ways that we've looked at this is, if you look back over the past year, Edge at this point has had 56% fewer RCE CVEs compared to Internet Explorer. And if you look at the past 6 months compared to the previous 6 months, Internet Explorer RCE CVEs are down 40%, half over half. So mainly due to MemGC. So these are examples of how we made changes, and then we measured the results, and we were able to see the impact of the work that we did. So we assume that we aren't going to be able to get rid of all vulnerabilities. There are going to be vulnerabilities that are present. So the second tactic that we follow here is we want to look for ways to break the techniques that attackers rely on when they're developing an exploit for a vulnerability. And the goal here is we want to increase the attacker's cost of developing a reliable exploit for any vulnerability that may exist. So a little bit of background. If you look at way back when to now, it's become a lot more difficult to exploit vulnerabilities that do exist. The CVE here from 2003 cites an exploit, a really bad exploit that I wrote back then. The exploitation was really simple. Trigger stack buffer overrun, overwrite return address to jump ESP, execute shellcode from the stack, arbitrary native code execution. It was that simple. Now, things have changed a lot over that time. So with Windows Vista, we enabled ASLR, and that got rid of most of the predictable image mappings that exist. So that broke one part of it. Later on, Internet Explorer in 2009, Internet Explorer 8 enabled DEP. So this killed off that heap spraying of code. And this was really kind of as we see at the end of what we think of as the code heap spraying era. Now, shortly after that, in 2010, we saw exploits start relying on DLLs that hadn't opted into ASLR. So we call these non-ASLR DLLs. And they were using that to bypass ASLR, and they were then using ROP to bypass DEP. Now, in Windows 8 and IE10, we added support for a feature called Force ASLR. And this was a way for a process like IE to go and make sure that all images were randomized. And this really did eliminate all of the predictable image mappings that existed. So this is kind of the end of the point for the non-DLL ASLR bypass era. Now, later that year, Furman Cerna gave a nice talk at Black Hat 2012 where he talked about the info leak era of software exploitation. And this kind of kicked off the what became the next part of software exploitation, which everybody has to rely on info leaks of one sort or another to be able to bypass ASLR. So now we're solidly in this era that we kind of consider the arbitrary read-write era, where if you look at the exploits that exist today, at least in the browser space, attackers rely on their ability to attain the ability to read and write to arbitrary locations in memory. I'm not going to read through the whole script that's on the right-hand side, but you can see there's many more steps that attackers have to, primitives that they have to satisfy to be able to develop a reliable exploit for a browser vulnerability. So that was a very brief summary of kind of the state of the art. Now I'm going to talk about some of the user mode mitigations that we've added to the platform. So the first one is 64-bit browsing by default. So when we go and analyze those exploitation trends, the number one technique that you see shared by pretty much every browser exploit historically was that they relied on heap spraying. And the way to think about heap spraying is essentially this code on the left-hand side, and this is taken from a Metasploit exploit. And what happens is, with this, they're basically just trying to fill up the address space. And if you look at a 32-bit process, it's really easy to fill up the address space because the address space is so small. But in a 64-bit process on Windows, the address space is 128 terabytes. And we have a feature that we added in Windows 8, actually, called high entropy ASLR. And this makes it such that there's 1 terabyte of variance in where basically the heap can start. So this really makes traditional heap spraying impractical. And what we did in Windows 10 with the Edge browser is we went 64-bit by default. So now we get to take advantage of essentially mitigating the classic forms of heap spraying. Now, when you look at the majority of Windows 10 devices, the majority of them are actually 64-bit. So most folks are actually benefiting from this. And what this means now is if an attacker does want to do some form of heap spraying, they need an additional information disclosure to be able to pull that off. Another mitigation that we added and enabled in Windows 10 is something that we call control flow guard. So when we look at most of the modern exploits, they typically rely on hijacking control flow through an indirect call as the start of their arbitrary code execution. So this is an example, again, from a Metasploit exploit where they hijack control flow by corrupting a virtual table pointer, pointing it into memory they control, and then they trigger a virtual method call that transfers control to the first gadget of their ROP payload. Now what CFG does is CFG implements what's known as coarse-grained control flow integrity for indirect calls. So how this works is at compile time, the compiler takes note of all of the functions that have their address taken. And these are functions that basically could be called indirectly at some point in time. And it embeds that information and metadata in the binary. And it also instruments prior to the indirect calls in the binary with a check that is going to make sure that whatever's being called is in that set of valid indirect call targets. Now at runtime, what we do is we actually, when an image is loaded that enables CFG, we actually kind of build up a big data structure for that process that tells us where all the valid indirect call targets are. And we map that into the address space of the process. And then when an indirect call happens, we do an O1 check against that data structure, and we see whether or not it's valid. And if it's invalid, we terminate the process. So that's at a very high level how it works. So what this means is with CFG in place, traditional ROP gadgets are not going to be valid indirect call targets, like your stack pivot gadget. And that means you aren't going to be able to take the approach that you've taken in the past to hijack control flow. Now, since we shipped CFG, there's been a number of interesting and great research that folks have published on bypasses, and we made a number of enhancements. So like all mitigations, there are corner cases and scenarios that things like CFG just aren't designed to mitigate against. So CFG doesn't protect return addresses. You can still call valid functions out of context. And we have a fail-open design for compatibility because we actually need existing software to be able to run. So since we've shipped it, like I said, researchers have come up with a number of interesting bypasses, and we've made changes to address those. So one of them was researcher Francisco Falcon pointed out that non-enlightened just-in-time compilers could be abused because they don't have the instrumentation in place. So this is something that's mitigated in Edge, where our JavaScript JIT, Flash, and the Warp software renderer all enable CFG instrumentation in their JITted code. There were also reports of non-instrumented indirect calls. These are kind of like mitigation bugs, where maybe somebody wrote an assembler and had an indirect call. We added, and we've addressed the ones that have been reported to us through our mitigation bypass bounty. As I noted, you can call other functions out of context, and some of those functions can be sensitive. So I'm not going to list all of these, but int continue and long jump, we've mitigated those. Virtual protect and virtual alloc in Edge on Windows 10, those are not valid indirect call targets. Load library is mitigated in Edge on Windows 10 through code integrity, which we'll talk about in a moment. And winexec, or trying to launch a child process, is mitigated in Edge on the Windows 10 Anniversary Edition, which was just released recently, by a child process policy, so you can't launch child processes. So these are ways that we've gone to address some of these. And finally, corrupting return addresses on the stack. This is something that we know is a limitation, and it's an area where we look to take advantage of future technology like Intel CET, which we'll talk about later, to help provide protection here. So we're continuing to look at ways to improve CFG, but we really do see it as kind of an important part of our mitigation strategy all up. Another area that we've invested in is code integrity and image load restrictions. So these are designed to try to prevent execution of arbitrary native code. And so typically the way that this works is exploits can try to cause a DLL to be loaded that it's malicious. They can change their arbitrary code, and they can use this for arbitrary native code execution. So on Windows 10, we allow processes to enable code integrity and image load restrictions to prevent these malicious DLL loads. There was a nice presentation by Yang Yu at Black Hat USA 2014 where he talked about basically a DLL planting technique that was a way that you could use it in conjunction with exploitation to cause an arbitrary DLL to be loaded. But in Edge on Windows 10 or other processes that enable this, this is now locked down to only allow properly signed images to be loaded, such as Microsoft WCL signed images. And so now the attacker can't cause their malicious DLL to be loaded. And we also prevent binaries images from being loaded from remote devices, such as UNC and WebDev. An additional benefit, not just security, but for reliability, is by preventing these image loads, we actually improve the reliability of the software, because a lot of the crashes in our applications come from DLLs being injected that shouldn't be getting injected into the processes in the first place. To help complement those code integrity restrictions, we have another feature that this was actually added in Windows 8.1, but we're continuing to kind of ramp up the scope that we enable it, is what we call dynamic code restrictions. And the way to think about this is nearly all of the exploits rely on creating new executable code pages to contain their shellcode. And so in Windows 10, processes can opt in to a mode that allows you to prevent new dynamic code from being introduced in the process. And the properties of this are, one, code is immutable, so existing code pages cannot become writable. You can't change them. And secondly, data cannot become code. So if you did have a read and write page, you can't then flip that to become an executable page. If you combine this with the code integrity and image load restrictions, this prevents all forms of unsigned code from being injected within the process. So this is a pretty powerful combination. So those were some of the user mode changes that we made and kind of the basis for why we made some of them. I'm going to shift gears and talk about some of the kernel mode features that we've added. So first off, in Windows 10, we have a technology that we call virtualization-based security. And it's really kind of a broad set of technology, but it has some important properties when it comes to exploit mitigation. So what this is when you enable Hyper-V on Windows 10, you actually get an additional suite of robust features to help protect the host and the guest kernels that run on that system. And the architecture that allows us to do this is something that we call virtual secure mode. And so the way to look at this is on traditional Windows, you have normal mode, and we call this VTL 0. And this is your normal user mode and your kernel mode. There's kernel data, there's user data, and there's that existing trust boundary there. But with VSM, what happens is, first of all, we have the hypervisor, which is a new security boundary. And then we have a completely different trust domain called secure mode, which runs in VTL 1, which is completely isolated from the normal mode VTL 0. And this allows us to robustly enforce some pretty interesting security features. So some of the mitigations that are enabled by this are, one, HyperGuard. So for some of you may be familiar with PatchGuard. This is our kernel patch protection software on Windows. HyperGuard is the hypervisor equivalent of that. And what's nice about HyperGuard is we can actually prevent modification of key MSRs, control registers, descriptor tables, and things like that. A concrete example is, and some folks notice this, if you are running with this enabled, you can't turn off SMEP. You can't flip the bit in CR4 and turn off SMEP because this is actually, it causes an intercept and we can block it. Another important mitigation that is enabled by this is something we call hypervisor enforced code integrity, or HVCI. And what this means is only signed kernel pages can become executable. Even if you can read and write anywhere in kernel mode, you actually can't defeat this because it's enforced by the hypervisor and VTL1. So these are really powerful mitigations. Another set of improvements that we made are to 64-bit kernel ASLR. So historically, the kernel address space layout on 64-bit has had a number of predictable regions. And what we've done in Windows 10 in the most recent update is we've actually gone and made the 64-bit address space dynamic. And so what this means is a bunch of the regions that were traditionally at fixed locations are now dynamic and randomized. So non-page pool, system cache, PFN, and most importantly, page tables. There are two papers, good papers that we cite here that talked about how you could abuse the fact that page tables were located at a fixed address on Windows. This is now mitigated because we randomized the location of the page tables. If you're curious a little bit about how that works, it's neat. We don't have a lot of time to spend on it, but basically we changed kind of the binary file format to allow us to retain the exact performance of how we did our kind of static page tables, but basically relocate them at the time that the image is loaded. Pretty cool piece of technology from the folks that worked on it. Another thing that we do is, if you're familiar with SIDT and SGDT, these are instructions that can actually leak kernel mode addresses. But when the hypervisor is enabled, we can actually trap these, and we can mask these so that you don't leak kernel mode addresses. So this is a cool mechanism that we have in place. And we've also made changes to the GDI shared handle table to make sure that these no longer disclose kernel mode addresses. So this is designed to really help up the bar in terms of exploiting kind of remote kernel vulnerabilities. So we're not going to spend any time on this slide. There's a link at the bottom, and you can read the slides afterwards. But these are some pointers for how to go and enable some of these opt-in mitigations for your application or your system. So I mentioned, we assume that there are going to be vulnerabilities, and furthermore, we assume that people are probably still going to be able to exploit them. So we look for ways to effectively isolate and contain the damage if someone is able to exploit a vulnerability. And the way to look at this is we want to increase the attacker cost of effectively leveraging an exploit for a vulnerability. So many of you may be familiar with App Container. This was something that was introduced in Windows 8, and this is kind of our platform sandboxing and isolation technology on Windows. So on traditional Windows, you have the kernel and you have a Win32 process. With an app container, like for a store app, this becomes much more isolated and contained. So some of the things that we've changed is in Windows 10, it used to be the case that font parsing was done in kernel mode. And a lot of people asked why we did this, and that's actually changed. So in Windows 10, font parsing has moved into a user mode app container that's isolated from everything else on the system. So if there is a vulnerability in font parsing, it's now contained within that sandbox. Another thing is for Edge, what we do is we actually have what we call a multi-app container model, where there's a manager app container and a content app container, and they're separate from each other. Now, what's new in the new version of Windows that we just released, 16.07, are a couple of things. So one is we've actually moved Adobe Flash into its own app container. So now it's isolated from both the content process and the manager app container. And what we've also done is we've actually enabled system call filtering for Win32K, which we observed was a big source of kernel EOPs for us for the content process. So app containers have a number of interesting security properties. They're a security boundary that we defend and will service. It's capability-based resource access. And app containers benefit from additional lockdown protection where we don't trust symbolic links that are created by app containers. There are a number of other things that we do specifically to lock down app container processes. So lastly, limiting the window of opportunity to exploit a vulnerability. If everything else fails, we want to make sure that we have effective tools and processes in place to limit the scope and the window of time that somebody can actually effectively leverage an exploit for a vulnerability. And this is really about minimizing the attacker's ROI if they are able to get past all these other hurdles. And very briefly, the way to think about this is kind of three slices. So one is we want to be able to rapidly respond. And so our incident response teams at Microsoft are really top of the line in terms of being able to mobilize our engineering teams to quickly resolve something. We want to rapidly protect. So one of this is we added a feature to Smart Screen that allows us to do synchronous blocking of URLs, drive-by protection. This is something that we can use if there is an exploit in the wild. And we also enable our Microsoft Active Protection Program partners, MAP partners, to protect the broader ecosystem if we know if there's an attack in the wild. And finally, and maybe most importantly, is being able to rapidly update. I think this is one of our most powerful features is that we have a well-tuned system for rapidly getting updates out to folks and getting them installed to really drive down the size of that affected population. So to conclude, one, security is more than just the code that you write. You have to think about it kind of vertically and everything that you ship in the product. So as Dave mentioned, we apply our strategy beyond just the code that we write in Microsoft, and we work with our partners to improve Windows platform security. So as Dave mentioned, we worked with Adobe very closely to try to take some of our experience to help with hardening Flash Player. And we've also been working with Intel on the design of their control flow enforcement technology, which provides things like indirect branch tracking through in-branch, and also provides a hardware support for a shadow stack, which is very exciting. So these are areas where we've looked to kind of work with our partners to help improve the platform all up in terms of security. So in terms of measuring our impact, we provided some data as we've been talking, but I think this shows that we have made measurable progress in terms of improving customer safety with respect to software vulnerabilities. If you look at some of the stats, these are just a few of them, but the number of Microsoft vulnerabilities exploited within 30 days has continued to decline year over year based off what we've observed. In the last 2 years, there hasn't been a zero-day exploit RCE for Microsoft RCE in the wild that's worked against Internet Explorer 11 on Windows 8.1 Plus because of the mitigations that exist there. And it's been about a year since we released Edge, but in that time we haven't seen any 0 days in the wild thus far. So we think these are all indicators of we are making good steps in the right direction, and we think we're positioned in a good place. Windows 10 and Edge are always up to date, so this means that we can keep revving and providing strong defenses for folks that are on the latest and greatest platform. And the data-driven approach and the red team assisted approach that Dave talked about really position us strongly to try to be ahead of the game as much as possible so that we aren't just reacting when we see exploitation in the wild. So one last bit to highlight, a bit of exciting news is we actually are launching a new bounty program for Microsoft Edge RCE vulnerabilities that affect the Windows Insider Preview program. We're not going to spend too much time talking about it in our talk, but you can find more details on our blog. But this is basically launching today, and if you find vulnerabilities, RCE vulnerabilities that affect Edge and the Windows Insider Preview slow build, you can get a bounty for it. So some exciting bit of news for folks that want to participate there. So with that, that's all we have.